Now that we've put some time into discussing how to solve a polynomial or how to solve a rational equation, we can kind of take the next natural extension of that, which is to solve inequalities. Now, when we talk about an equation, what we're usually saying is we set some kind of expression, maybe something like x squared minus x, equal to another kind of expression. And on the left here, I've written a polynomial. On the right here, I've written a rational expression. But this is all just general. The idea is that we want to figure out what values of x will make this expression on the left equivalent or equal to this value on the right. That's why we call them an equation. An inequality, though, an inequality is just a little bit different. Instead of figuring out what values of x make the two expressions the same, we want to figure out what values of x make those two expressions unequal or different, but in a particular way. So maybe that is, well, what values of x make x squared minus x greater than x plus 1 over x minus 3? Or less than, or greater than or equal to, or less than or equal to. And so any of these four possibilities will make what we call an inequality. And if you think back to an algebra class, it's likely that you've solved some of these already. Right? Maybe something of the form like negative 5x plus 7 greater than negative 8. And this was something that we could solve by following a lot of the same techniques that we would use to solve as if it was an equation, just with one exception, right? We would subtract 7, for instance, to try to isolate x and get negative 5x is greater than negative 15. We would divide by negative 5 from both sides, just like we would in an equation, and we would get x. And this is the piece where we'd have to change it around a little bit, right? Because since we were dividing by a negative number, we would have to flip the direction of that sign. So rather than being a greater than sign, we would switch it to a less than sign. But otherwise, everything would proceed the same. Negative 15 over 5, that's going to give us positive 3. And so this would give us a solution of x is less than 3. And we would typically write this in interval notation. So less than 3 would be everything from negative 3 up to 3, and using parentheses here because we are not including our value of 3. We're not including the endpoint. It's not a less than or equal to. And what this represents is all of the x values that if we were to plug them back into this inequality would make this statement true. That would make this side of our inequality greater than this side of our inequality. And of course, you could plug those in and check, and this would work exactly the same way as an equation. However, just like how polynomial equations required some additional skills and techniques in order to solve beyond just the same types of skills and techniques we would use to solve a linear equation, we're going to have to apply some of the techniques and skills that we've learned over the past few videos to solve polynomial and rational inequalities instead of just linear inequalities like this one as well. And so the first thing we can actually do to start to get a feel for the big picture of this, how this is going to work in kind of the grand scheme, is to look at graphs. And so if we think about a polynomial's graph, which we have pictured here, there's a few important things that we want to recognize. The first is that they are all continuous. And again, we talked about this in a previous video, but essentially what this means is that you can start at the beginning of the function and draw the entire thing without picking up your pencil. It has to be one continuous line. And the second thing that we can note here is if we use this x-axis as sort of like an anchor point, a base point, it's really easy for us to see on the graph what regions live above that x-axis and what regions live below that x-axis. And this is going to be important in terms of how we go about solving these polynomials, right? It's easy for us to identify when is this positive, like in all of these three regions here, and when is this negative. And in particular, we've spent a lot of time studying specifically how to figure out when the graphs of polynomials intersect that x-axis. We called those zeros. And so we're going to utilize this idea of being able to recognize when f of x is equal to 0 to then tell us, well, when is it greater than 0, like when is it positive, or when is it less than 0, or when is it negative. And using that as sort of an anchor, we're going to be able to solve a variety of inequalities in this way. And rational functions are not so different. Yeah, we have some different features like a vertical asymptote, and these functions are not continuous, right? We can't draw a line through here and then come to here without picking up our pen. And this is going to be important here too, because kind of like polynomials, having these certain spots where interesting things, we'll say, interesting things like a vertical asymptote or a zero happen, those are going to be the key places for us to pay attention to in terms of when can this graph cross this x-axis, right? If we think about when the graph can cross the x-axis, we can realize that this can only really happen in two instances, right? This can happen at a root, or just like we had with the polynomials here. So this can happen at a root, or this can happen like in this case here, where we are going from positive values to negative values at a vertical asymptote. And so in both of these cases, what this is really going to come down to is framing this in a way that we can make a comparison to the x-axis and ask, when is our function sitting above it? In other words, when is it positive? And when is our function sitting below it? In other words, when is it negative? And utilizing, in the case of polynomials, those zeros, those roots, or in the case of rationals, the roots and the vertical asymptotes, we'll be able to decide when it's either above the axes or below, since it can only cross in those specific situations. And so in terms of generalizing the process of how we might try to solve these, keeping that big picture in mind, we always want to compare to 0 because we have all of this information about roots and asymptotes, and this is where the function's sign can change. Comparing to 0 is always going to give us a good way to start out these problems. In other words, we want an inequality in the form either f of x greater than 0 or f of x less than 0, right? Or greater than or equal to or less than or equal to. But the point is we always want to compare this to 0. So for instance, if we had the case of x cubed plus x squared minus x greater than 5, we would want to make sure we move that 5 over to the other side by subtracting it to give us x cubed plus x squared minus x minus 5 greater than 0. Right? And this greater than 0 piece is going to be the key to helping us utilize the concepts we've discussed previously in order to find a solution. Now, the second piece of this is to actually utilize all of those concepts that we've learned about roots and vertical asymptotes in order to determine where are the places where it intersects the x-axis. In other words, where are the places that the graph can potentially change sign? And these we'll call the critical points. So we'll want to find the critical points, right? In other words, the roots, the vertical asymptotes, specifically whenever f of x is equal to 0. So in solving the inequality, we're actually going to solve the equation for when our function is equal to 0. And that's going to give us the values at which our graph can potentially change from positive to negative or negative to positive. It can flip from being greater than 0 to less than 0, or vice versa. And then we can use what's called a sign chart to keep track of this. And now that sounds like a fancy term, but basically what this means is we're gonna draw a number line and we'll plot those critical points. So let's say that we had our equation f of maybe 3 was equal to 0 and maybe f of 5 was equal to 0. Then we can plot those points on our number line of 3 and 5 because these are the values where our function could potentially change from positive to negative or from negative to positive, allowing us to determine where our function is either greater than 0 if that's what we're looking for, or less than 0 if that's what we're looking for. And next we can start to test values within each interval. Since these are the only values here that the sign can change, it's the only time we can transition from a positive to a negative or vice versa. If we picked a number in here, say maybe like 2, and we plugged in f of 2 and found that that was equal to, I don't know, say maybe something like 10, in other words, a positive number, then we know that everything within this interval here, so everything within this space, would have to be positive. Maybe then we plug in something in our next interval between these two critical points, maybe something like 4. If we found that to be maybe a value like negative 10, well, that's going to tell us that everything in this region here is negative, right? It has to be everything because otherwise there would be some other point in here where our functions switch signs, some other critical point. And then we can do the same for the last region too, right? And so maybe we plug in f of 6 and we get something like 7, right? And so we find that this ends up being positive. And what that tells us here, and then what that allows us to do in terms of writing our solution, is to say, well, everything in this region and this region are greater than 0. So if we're solving for when it's greater, we can use those two intervals. And everything within this region is less than 0. So if we were solving for when it was less than 0, we would use this region between 3 and 5. And so all that would be left for us to do is to write the solution as an interval. So for example, if we were trying to solve for when f of x was greater than 0, that would tell us that our solution lives here and here. In other words, we have to include the interval from negative infinity to 3, along with the interval from 5 to infinity, and we'll union those to form one single solution. But that's enough about the general process for now. Keep these big ideas in mind, but I think it will help for us to actually work through a concrete example here, to get a feel for how we can apply these ideas of identifying those key points where we could potentially change sign and comparing this to 0 in order to actually solve some inequalities. So let's look first at x squared minus x is greater than 20. We know that the first thing that we want to do here is compare to 0. So we need to write this in the form of f of x is greater than 0. In other words, we have to get this 20 that's off by itself on the right-hand side over to the left-hand side and leave just 0 here on the right. And that's not too bad, right? We know we can just subtract 20 from both sides, and if we do that, then that's going to give us x squared minus x minus 20 on the left greater than 0 on the right. And so now that we've anchored everything around 0, we want to figure out, well, when is it above 0 and when is it below 0 to help us solve this inequality? So finding those points where it can change, in other words, those points where f of x is equal to 0, is going to allow us to do that. It's going to allow us to find those points. And so we'll solve for when f of x is equal to 0. In other words, we need to solve for when x squared minus x minus 20 is equal to 0. And there are a number of different techniques that we've discussed in terms of how to do this. We can use factoring sometimes, we can use the quadratic formula, we can use the rational root theorem. There are a lot of techniques that we have in order to solve equations like this, but that's going to be our next step. And so in a case like this where we just have x squared and no coefficient, we can do some factoring here and recognize that we just need a pair of numbers that multiply to -20 and add to -1. Specifically, those would be -5 and +4. And so we can factor the expression x squared minus x minus 20 to be x minus 5 the quantity times x plus 4 the quantity equal to 0. And then we know by the zero factor property that this means that either one of those factors would have to be 0. So x minus 5 equal to 0 or x plus 4 equal to 0, which allows us to solve this as x equal to 5 or x equal to -4. And these values here represent our critical points. And that's because, again, since a polynomial is continuous, the only time it can change sign is if it crosses through the x-axis. In other words, if it passes through a value where it equals 0. So for this polynomial, x squared minus x minus 20, to pass from positive to negative, or maybe from negative to positive, that can only occur when x is equal to 5 or when x is equal to -4. And so using those values, we can now draw a sign chart. In other words, we can draw a number line where we label -4 and 5 to break up our real number line into these three intervals. And knowing that these two values are the only places where this can change sign, we'll want to check for what the sign is here, what the sign is here, and what the sign is here. And so we'll check the signs of values at maybe, say, f of -5 and f of 0 and f of 6, because -5 will represent this region, 0 will represent this region, and 6 will represent this region. And so if we plug those values in, if we evaluate our function at those different values, -5 would give us -5 squared minus -5 minus 20, or in other words, 25 plus 10 minus 20, or 15, which would be a positive number. And so we'll go ahead and write a plus sign here to represent that every value in this region is positive. Plugging in 0, we have 0 squared minus 0 minus 20, which will equal -20. And so that tells us that everything in this region matches the sign of -20, in other words, is negative. And lastly, f of 6 will be 6 squared minus 6 minus 20, which equals 36 minus 6 minus 20, or in other words, 10. Since 10 is positive, that represents this whole region here, and so we can put a plus sign there to say that everything in this region is positive. Copying our sign chart here, we can then go on to our last step, which would be to write the solution as an interval. And now, since we're solving for when f of x was greater than 0, what we're looking for on this sign chart is what regions are going to be positive, what regions sit above the x-axis. In this case, that's going to be here and here. And so we just have to express this as an interval. Now, we have the region from -infinity to -4, right? That's everything here to the left of -4. And then we also have the region 5 to infinity. That's everything to the right of 5. And so all we'll have left to do is to combine those into one single solution by using a union. And so we have -infinity to 4 unioned with 5 to infinity as our final solution. Now we can apply that same sort of technique to solving rational inequalities as well. The only difference is that in addition to finding the roots, we also have to consider the vertical asymptotes, because a rational function is not continuous, at least not always. And so it can also change sign. It can also jump from above to below the x-axis in the case of a vertical asymptote. In any case, our first step is to compare to 0. And so we'll want to do a little bit of algebra here to get this in the form of f of x is greater than or equal to 0. And so if we start with 2x over x plus 1, greater than or equal to 1. We can do this by subtracting 1 from both sides. However, this is going to take an additional step compared to the last problem, right? Because now we have 2x over x plus 1 minus 1 is greater than or equal to 0. But since this is not a single fraction, it's going to make it hard for us to figure out what the roots are and what the vertical asymptotes are. And so we'll need to do some simplification here by finding common denominators. And so specifically here, we can leave 2x over x plus 1 by itself, since minus 1 is just minus 1 over 1. But then we'll want to subtract 1 multiplied by x plus 1 over x plus 1. Because in this case, that x plus 1 is the least common multiple of the two denominators. And so multiplying that out, we'll have 2x minus x plus 1 divided by x plus 1, all greater than or equal to 0. And notice here I'm being careful with my parentheses because we are going to have to distribute that negative. That's an important thing to be aware of here. But once we do that, we can then, and I'll bring this up over here, we can then do the rest of the simplification and say 2x minus x minus 1 over x plus 1 greater than or equal to 0. Or more simply, x minus 1 over x plus 1 is greater than or equal to 0. And so now that we have this as an expression greater than or equal to 0, we can use this to find the critical points. In other words, we're going to look for both the roots and the vertical asymptotes, which I'll just abbreviate here as VA. We know that solving for the roots is just about determining when the denominator is equal to 0. And so x minus 1 over x plus 1 is equal to 0 when x minus 1 is equal to 0. In other words, when x is equal to 1. And x minus 1 over x plus 1 has a vertical asymptote when the denominator is equal to 0, right? In other words, when x plus 1 is equal to 0, which we can solve to be x equal to negative 1. And so with critical points of x equal to positive 1 and x equal to negative 1, we can then form a sign chart. We can plot our value of negative 1 here and our value of positive 1 here. And then just as we did before, test the values in the intervals between them. So test a value from this region, test a value from this region, and test a value from this region to determine the sign. And so for instance, we might pick a value like negative 2 to represent this region here. We might pick a value like 0 to represent this region here, and might pick a value like positive 2 to represent this region here. And so if we plug in negative 2 to x minus 1 divided by x plus 1, we'll get negative 2 minus 1 in the numerator, or negative 3 divided by negative 2 plus 1 in the denominator, or negative 1, giving us positive 3, making this whole region here positive. Plugging in 0, we'd have 0 minus 1 over 0 plus 1, giving us negative 1 over 1, or simply negative 1. Since negative 1 is negative, that represents this whole region here, and so everything between negative 1 and 1 will be negative. Finally, inputting 2, we have 2 minus 1 divided by 2 plus 1, which gives us 2 minus 1, or 1 for the numerator, and 2 plus 1, or 3 for the denominator, in other words, 1/3. Since 1/3 is positive, this entire region here would be positive. It would be above the x-axis. And so now that we can see all of this region is positive and all of this region is positive, all that we have left to do is to write our solution as an interval. And so just like the last one, we might recognize that this whole region here can be represented by negative infinity to negative 1, since it's everything to the left of negative 1. And this whole region here can be represented by 1 to infinity. And then since we want to take the whole solution, we'll just union those. And we might think that that's good enough, but we have to hold on and think a little deeper for just 1 second here, right? Because in this case, we aren't just looking for when f of x is greater than 0, right? This is all positive here and all positive here, so it's greater than 0 in those cases. We're specifically looking for when when f of x is greater than or equal to 0. So we could potentially use those roots as values where it's equal. So these endpoints here, these boundary points might matter. In other words, we might need to use a square bracket in one or more of these instances. And that doesn't also mean just replace each of these with a square bracket and call this a day, because in actuality, only one of these values can be included in our solution set. So the question is, which one? Well, one of these values is a root. In other words, it intersects with the x-axis. And so as it crosses from positive to negative, as it makes that switch, it does in fact equal to 0. The other value, though, is just at an asymptote. And so when it switches from positive to negative at that asymptote value here, well, it doesn't actually cross 0. There isn't actually a defined value here at whatever that value was, wherever the vertical asymptote is. And so we can't include a vertical asymptote in our solution, but we have to include a root if we're talking greater than or equal to 0, because the root is when it is equal to 0. And so in our case here, because x equal to 1 was our root, we have to put a square brackets here and a parentheses here. We use the square bracket to signify we're including the root when the function is equal to 0, but we'll use the parentheses here because we can't include the vertical asymptote because it is not equal to 0. It is in fact not even defined. And so this would represent our final answer. And in general, this will represent the process for which we can solve polynomial and rational inequalities. If we can compare them to 0, if we can use that x-intercept as our guide, we realize that there are only a few certain values at which our function can change sign, from which it can change from positive to negative or negative to positive. For polynomials that are continuous, that's only at the roots. And for rational functions that have some discontinuities, that occurs at the roots as well, but also at the vertical asymptotes. And so by solving for those critical points when f of x is equal to 0 or when f of x is undefined, then we can determine when our function is positive and when it's negative, and then ultimately decide whether it's greater than or less than, or greater than or equal to or less than or equal to 0, and ultimately solve our polynomial or rational inequality. I hope you found this video helpful. As always, if you do have any questions, please reach out. This will probably be one of those types of problems that takes a few reps before you start to get the process down. So make sure you're getting practice both with notes in front of you and without notes in front of you, so you know not only that you can follow along with the process, but that you can generate it on your own. And the more you practice, the better that you'll get. But anyways, thanks for watching, and I hope you have a great rest of your day.